Hey everyone and welcome. Today we are going to unlock one of the most powerful tools in your calculus toolkit, the Binomial Series. This is the key that lets you tackle functions that, honestly, look pretty much impossible at first glance. So let's jump right in.
You've been expanding things like a plus b squared since what, your first algebra class? It's pretty straightforward, you know the drill. But what happens when the rules of the game change? What if someone asks you to expand something like the square root of 1 plus x? All of a sudden, those standard algebraic tricks, well, they just don't work anymore.
And yeah, this is the real heart of the problem, isn't it? What on earth do you do when the exponents aren't nice, neat, positive integers? We're talking fractions or even negative numbers. This is where calculus comes in and gives us this absolutely brilliant way to think about it, and more importantly, a way to solve it.
And the answer is a really beautiful piece of math called the Binomial Series. I want you to think of it like a master key. It's a key that can unlock the expansion for any real number exponent. Doesn't matter if it's positive, negative, or a fraction. Okay, here it is. I know it might look a little intense at first, but it's actually incredibly elegant. The real game changer here, the thing that's different from basic algebra, is that exponent, k. In this formula, k can be any real number. What this does is it gives us an infinite polynomial, a series of terms that perfectly represents our original function, just as long as the absolute value of x is less than 1. Now, at the core of that formula is this thing, the generalized binomial coefficient. Don't let it intimidate you, it's just a pattern. For the top part, you start with your exponent k, then you multiply by k minus 1, then k minus 2, and you just keep going until you have n of those terms. The bottom is just n factorial. Let's actually see how this works.
All right, enough theory, let's put this into practice. We're going to tackle that exact question that stumped us at the beginning, finding the expansion for the square root of 1 plus x. So in this case, our exponent k is just 1/2.
Okay, let's build this thing one term at a time. So when n is 0, the coefficient is by definition always 1. That's our starting point. Easy. For n equals 1, it's just k divided by 1 factorial, which for us is just 1/2. So far, so good.
Now for the n equals 2 term, the numerator is going to be k times k minus 1, so that's 1/2 times negative 1/2. Then we divide that by 2 factorial, which gives us negative 1/8. And you really have to watch out for that negative sign. It's such a common spot to make a tiny mistake, but it is absolutely crucial to getting the right pattern.
And moving on to n equals 3. The numerator now has 3 terms, 1/2 times negative 1/2 times negative 3/2, all of that over 3 factorial. And when the dust settles, that works out to a positive 1/16. You can already start to see this really cool alternating pattern emerging, right?
So now we just put all the pieces together. We take each coefficient we found and multiply it by its matching power of x. And the result is that the square root of 1 plus x can be approximated by this polynomial, 1 plus x over 2 minus x squared over 8 plus x cubed over 16, and on it goes.
Okay, so the formula obviously works for fractions, but what about negative exponents? Let's run through one more example just to see how versatile this series really is.
This time, we're going to expand the function 1 over 1 plus x squared. But if we just rewrite that using an exponent, it's simply 1 plus x to the power of negative 2. So, for this problem, our k is just negative 2.
Now here's something really cool that happens. For certain integer values of k, that big, clunky binomial coefficient calculation actually simplifies into a much friendlier little pattern. When k is negative 2, the coefficient is just negative 1 to the n times n plus 1. This is going to make our calculations way faster. So using this little shortcut, we can just crank out the terms like it's nothing. At n equals 0, we get 1. For n equals 1, it's negative 2x. At n equals 2, a positive 3x squared. And for n equals 3, negative 4x cubed. Look at that. It's this beautiful, clean, alternating pattern of integers.
And there we have it. The full series expansion is 1 minus 2x plus 3x squared minus 4x cubed and so on forever. We just took another function that looks kind of complicated and turned it into a simple, infinite polynomial. Pretty cool.
So, we've seen how to use the binomial series, but let's just step back for a second and ask the most important question. Why does any of this matter? What's the real power behind this formula? So here's the #1 thing you should take away from this. The binomial series lets us take these difficult functions, things with square roots or weird fractions, and it transforms them into polynomials. And polynomials
Polynomials are our best friends in calculus. They are so easy to differentiate, to integrate, to just plug numbers into. This series gives us a way to approximate really complex behavior using simple, predictable, easy-to-work-with building blocks.
And that brings me to a final thought for you. So much of science and engineering is all about modeling really complex systems. So how can this one technique, this ability to swap out a difficult function for a simpler one that's close enough, how can that fundamentally change the way we solve real-world problems in fields like physics or electronics or fluid dynamics? It's a really powerful idea to think about. Thanks so much for watching.